remember the first DEF CON in 2017. It was not like this. And production value is so good now. Hey, everyone. Super excited to be here. My talk is titled The Chain Abstraction Master Plan. So I'll talk about a few concepts that we started a company to explore, and try to go into what we think we can achieve by using these things. So let's dive right into it. To set the context, I want to go back into sort of what I would consider the main phases of Ethereum and the challenges that we sort of had to explore and face along the way. Initially, when Ethereum came out, the idea was that it would be the world computer, you would have a synchronous environment, there would be one blockchain, and you would put everything on it. And so I would term this to be the big Ethereum stage of Ethereum. Then something happened in 2020, which is the chain ended up being unusable because gas prices spiked to an insane level. I think this was sort of the start of DeFi summer and yield farming and all this fun stuff. And so the new idea came out, which was let's actually put everything on a handful of rollups. And I would call this the big rollup phase of Ethereum. And then more recently, we've sort of seen that the rollups themselves started to split up into their own thing. And so now the idea is you have sort of an app that's on its own rollup, and so you have clusters of rollups. Now, my claim is that this is sort of fundamentally broken for all the reasons that people experience with fragmentation, and there's a particular solution that's needed to be able to enact it. And that solution is called resource locks. So resource locks is really the thing that One Balance was founded to explore and propagate. And our goal is to really bring this as a fundamental component to the entire Ethereum stack. So let's go into resource locks. Let's talk about intents, and let's talk about how it helps achieve atomic interop. This is a graphic of the resource lock stack. We published an article called The Cake Framework that explores some of this. The resource locks is just this piece in the middle here. So it's one of the many messages and interfaces that need to be introduced to be able to achieve a fully chain abstracted sort of endgame for Ethereum. And it only works when you have some of these other components that are being added to the system. The thing to notice here is that this is an intent-based architecture, right? So it uses solvers to be able to execute transaction on-chain on behalf of users, and then proving the execution back to wherever the execution originated from. Now, the magic behind resource locks is really what allows us to achieve this seamless interoperability in Ethereum. So let's go into talking about what a resource lock is. It's really composed of two things, and there's many shapes and sizes of resource locks. So it's finality protection and equivocation protection. And this is actually one of the core properties that blockchains offer. Just the problem is that blockchains offer it in a very, very expensive way. So if you sort of abstract away the concept of these two things, and then you add them up with the concept of an intent, which is specifying input state and output state, you can achieve something that we refer to as resource lock intents. And so this is what we sort of believe is a fundamental messaging format for anything that will be cross-chain if we want all of Ethereum and all chains to operate as a unified component. We can explore how intents and resource intents compare to some of the other interop approaches and their trade-off. So a canonical bridge, this is how do you pass a message between two L2s in the most secure way possible. You have to start the message on the first L2, send it through the fraud-proof mechanism, wait 7 days, and then pass it up through the canonical bridge on the other L2 for messaging. And the core thing you have to wait for here is full finality over the message passing, which is why it takes up to 7 days for optimistic rollups. How can we go faster? Well, one way that we can go faster is just be optimistic about the finality. So when you deposit crypto inside of a custodial exchange, you don't wait for the full finality oftentimes. You wait for some optimistic version of finality. So for an L2 deposit, usually you'll just wait for a single roll-up blob to be posted to the chain, and the exchange sort of considers that to be final enough to be secure. But you still have to wait for this sort of full roll-up blob to be put in. So how do we go faster? Well, intent bridges have become much more popular, which is an approach to actually send the message through a solver, have the execution happen on chain, and then prove that back to the origin chain that it was successfully included. The problem here is that you're still relying on the source chain for providing the resource lock, which means that you still have to have inclusion times on the origin chain before the solver can do the inclusion on the destination chain. So you're still fundamentally 2 inclusion times away from atomic execution. And then resource locks take away that requirement for execution on the source chain and says, actually, all you need is a signature from the user, and you can automatically and instantaneously go and execute on the destination chain. So this is sort of fundamentally the fastest way that you could do interop, because you're always operating at the destination chain speed. So this falls under the category of interop that we call sort of atomic interop, or atomic execution interop, as opposed to atomic inclusion or atomic composability. And I want to compare it with some of the other approaches that are being discussed for atomic interop. So if you look at sort of in-cluster interop between the ZK rollup land and the optimistic rollup land, you'll see some of this terminology come up. So AgLayer and Elastic are both ZK rollup clusters, and they are limited by some fundamental constraints. So one is the proving speed of the rollup itself. So you cannot send a message within this interop system faster than the proving speed of a ZK proof. And if you were to assume that you had real-time proofs, which is sort of like a standard that we're looking for, even that in that world, you're constrained by the fact that you can have cascading reorgs across 2 different rollups. So if, for whatever reason, the L1 that you're posting your blobs to or your proofs to ends up reorging away that blob, and you end up posting a different set of transaction, any other rollup within this interop ecosystem that's listening to that post will have to also reorg. And so you sort of have these the security assumptions that are conditional on other security environments. So it's not ideal. Superchain and ARB clusters have very similar sort of guarantee requirements. So it requires a super builder, which is just a sequencer that's going to be sequencing both any of the rollups that are being touched by the multi-chain message. And the implication of that is that you're completely foregoing chain sovereignty. Which means that every single rollup within this optimistic interop cluster need to behave according to the exact same rules and need to upgrade following the same assumptions. And so if you have, within the superchain environment, the unit chain and the base chain, any upgrade to the sequencer or their behaviors would have to be coordinated and have to be mutually trusted. Because the risk is that if the unit chain has a fault for whatever reason and produces an invalid message, it could cause also a reorg on the base chain. And so these cascading reorgs make it very, very difficult to achieve this in a scalable way. What about resource lock intents? Do these have any trade-offs? Well, yes, they also have trade-offs. While they're not susceptible to some of these reorg issues because of the resource lock nature of it, they are constrained by the liquidity that's available through solvers, and they also are susceptible to black swan risk. For example, if all the liquidity ends up moving in one direction at the same time, the liquidity providers could shut down, and you would be unable to actually execute the transaction that you're looking for. So where does sort of one balance fit in? Well, I hope I made a case for why resource lock is like a useful primitive for atomic interop between L2s. And our approach is really to provide a toolkit for any apps and wallets who want to benefit from this instant cross-chain execution to be able to do so. This provides basically the full chain abstraction experience for these wallets, right? A completely chain-free, bridge-free, and gas-free user experience. And we have an app that you can go and try out that has cross-chain swaps and experience what this feels like. The other product that we have is what we call resource locks as a service. So this is a product really tailored towards infrastructure providers. And it provides these guarantees of reorg and equivocation protection. It really allows for a completely trust minimize destination chain speed execution. We also implemented just before DEF CON what we call teleport. So this is a token wrapper for ETH that allows you to instantaneously send ETH to any other chain or rollup without having to wait for inclusion time. And so, yeah, it's a really cool way to be able to transact on any chain at the speed of that destination chain. I have this slide as a bit of a troll to a slide that we saw earlier this week, which is, I think it's important for us to be ambitious about solving the problems that Ethereum has sooner rather than later, and achieve sort of the UX gains that we want, given the environment that we're in. And so, what's the timeline for this? Well, it's already live, right? Like this chain abstraction stuff is sort of built out tech, and it's ready for anyone that wants to experiment with it and build it into their applications in prod for them to do so. And so, yeah, they encourage everyone that's thinking about operating and building apps or wallets to look into resource locks and understand what are really the benefits that they bring. So that's it. Thank you so much for listening to me.
Okay, we have 3 questions. So first question is, why does everything need to be fast as fuck? Can we leverage the better channel capacity usage by load balancing?
Fast as fuck is the optimal goal, right? You could say that, like, what is the actual time that you're looking for from like a UX perspective? I think like a 2-second goal of like being able to execute is pretty good. Now you can say, okay, can you achieve that through like regular other channels that I've described in the framework? Maybe, but you're still susceptible to all of those trade-offs that I explained. And so even if you have like seemingly faster channel messaging, you still have a bunch of trade-offs included, which is why I think resource locks on top of it will always be used.
Okay, the next question is, do relayers need to have liquidity on every chain and rebalance accordingly, and is this a problem?
Yes and no. So instead of relayer, I like to use the solver terminology. And you can have solvers that have inventory, which you would refer to as market makers, or solvers that don't have any inventory. And the ones that don't have any inventory essentially pull the liquidity from liquidity pools on destination chains. The other thing that you can have is you can have native bridged assets. So realistically, the majority of the volume when you go in a cross-chain setting is going to be ETH or some stablecoin. Stablecoins benefit from being natively mintable on any of the chains, and so you don't actually need to hold inventory on that token in those chains. You can instantly mint it there. And there's also work being done on the ETH side to be able to make canonical minting of ETH on any rollup. And that will also prevent the need from having inventory on those rollup for solvers.
Okay. What are the security guarantees of source chain signature validation by the relayers on the destination versus systems like 7683, and why should we trust this more?
Signature validation by the relayers on the destination versus system. Okay, I don't get the middle part of this question, but I can say, like, okay, what's the difference in the resource locks between an intent bridge and a resource lock bridge? So 7683 is like this intent standard, and it provides some of the fields that you would have when you're trying to do resource lock resolution on chain. I think it doesn't specify anything about the commitments that are being made about the state of the account when you're inputting it. It just so happens that right now we're doing this by putting it on the source chain, but there's a bunch of mechanisms that you can do to secure resource locks that are fully off-chain. I won't get into them in this presentation, but I would just point you to our ETH research post about resource locks.
Okay, seems the time's up. That's it. There are more questions, and you can find him here.
Thank you.
Thank you.